A triangle ABC angle bisector AD, and D is on the circumcircle. And then we have discovered one thing from last time, AB times AC equals AE times AD. Okay, this times this equals this one times this one, right? We proved it last time. Now there's another pair of interesting things which says DC square equals DE times DA. So this square equals DE times DA. The reason is very simple, because this triangle is similar to this one. The small one is similar to the bigger one. Why is that? It's because this angle equals this angle equals this angle equals this angle, right? All these four angles are the same. So now this angle equals this particularly, right? So triangle DCE is similar to DAC. All right, so DC square equals DE times DA. And similarly, you have DB square also equals DE times DA. Right, because first of all, DB equals DC, right? DBC is isosceles. And in the other hand, this triangle is similar to this one, right? Same reason, right? Because this angle equals this one. Okay. Another interesting segment could be calculated. So now, here's the thing. Combined with what we have learned last week. So right now we have AB times AC equals AE times AD, right? And then, but then we also have DB times DC, which is, you could write it as DB square, or you can write it as DC square, right? This equals DE times DA. Now, if you add them up, AB times AC plus DB times DC, this equals AD times AE plus DE. This is basically AD times AD, or should we just say it's AD squared? All right, that's an interesting property. So basically it's saying that AD squared minus DC squared, for example, equals AB times AC. Right, something like that. All right, so just such a simple configuration, right? Just a simple angle bisector. We made a whole lot of things out of it. No, similar triangles, segment products and squares and all that. And let's put everything in action. All right, let's look at a problem, which is supposedly a difficult problem. Let's look at this one. 2012, AMC 12A, problem 16. Let's see what it's talking about. Circle C1 has its center lying at circle C2. So let's see. Like this. This is O, this is C1. This is circle C2. The two circles meet at X and Y, okay. And again, if you are watching this video, I suppose that you should freeze it and spend a couple of minutes trying to solve it on your own, all right? You see, most of the time, the geometry problem does not have a graph, and we supposedly have to draw it ourselves. Let's draw the proper graph, all right? Meeting at X and Y, Z is an exterior of C1 out of C1, which lies on C2. So let's just say it's here. XZ equals 13. OZ equals 11. YZ equals 7. What is the radius of C1? What's the radius of this small circle? All right. I suppose that I'll give you a couple of minutes. And if you're watching this solution, well, is there an angle bisector somewhere? Well, just given this right now, we don't have a lot of triangles right now, right? Technically, I don't even have one triangle yet, unless I connect some lines. I see that the triangle potentially XYZ, there might be triangle XOZ, YOZ maybe, but there is an angle bisector, do you realize? For example, if I connect this, I connect this one, I connect XY, I connect XO, and I connect OY, okay? Do you see angle bisector now? This angle equal this angle. But why? Well, it's because if you think about it, triangle XYZ, its circumcircle is C2, right? And then on C2, there is XO equal YO. These two chords are the same. So these two faces the same angle. All right, so OZ bisects angle XZY. All right, it's a very skinny looking triangle, but regardless, that's an angle bisector. Now what? We're gonna use our little property, right? Well, ZX times ZY, this is both of them I know. I know ZX, I know ZY. I would like to try my little property, see where it can get me. This time this supposedly should equal Z, call this point P, all right? Supposedly this should equal to ZP times what? ZO, right? So this is 13 times 7 equal ZP, which I don't know, times ZO, I know that, 11. ZP equals 91 divides 11. All right, so if ZP is known, then all right, OP is known, no? OP is 11 minus that, right? So it's like 30 over 11. All right, so wait a second, what are we looking for? We are looking for the radius of C1. Allow me to maybe highlight. We are looking for XO, right? Or maybe YO, right? These two segments, these are the radius, right? Well, remember the second property we just learned today, XO square, which equals YO square, equals what? Equals OP times OZ, right? Can you recognize that? I mean, just because I have this triangle XYZ as a, obtuse triangle, the angle is kind of skinny. It makes you make the graph a little bit unrecognizable, right? But it's the same configuration, right? It's basically the angle bisector meeting the circumcircle, all right? Let's recognize that. And then once you have that, so you should recognize this right now. XO squared equals YO squared equals OP times OZ, all right? And so let's plug in. OP is 30 divides 11. OZ, what is it? Oh, it was 11. Okay, 30. Looking for the radius. That's the radius square. Square root of 30. All right. Does that look interesting? You know where the difficulty of this problem lies in? I think one of the difficulty lies in the fact that the graph is unrecognizable. If you're very familiar with this graph right here, right? Such a nice, acute triangle, angle bisector, everything looks very pretty, right? Now, that's how we learn the theorem, right? But in the real, application, the triangle is obtuse. The angle XYZ is kind of small. So the angle bisectors are kind of very skinny, very sharp. The graph is not very clear. Now you have to kind of zoom in, right? So, well, that creates a little bit of a difficulty here. But that's why you need to practice and get to recognize all these configurations. All right. Okay. Thanks for watching. And if you like what you're seeing, please subscribe for more updates. Thank you very much. See you next time.